What's up everyone? In this video we're going to be going over density. So this is a new definition for us, and density can be described as how tightly a material is packed together inside of a 3D figure. And the more packed the objects are inside of the figure, the more dense that figure is going to be. So I like to think about packaging an Amazon box. So let's say we're packing basketballs and we're shipping them out. Let's pretend all of these 3 Amazon boxes are the same exact size. And let's say for one example, we have to ship out 7 basketballs, and we're packing those in the box. In another example, we're packing 3 basketballs, and then in another example, we're just packing 1 basketball. So, since we're packing 7 basketballs in the same sized box here, this package is going to be very dense. We're really tightly packing it in together. Whereas this middle example, we're packing 3 of them, so it's a lot less dense than this 7 basketball example. But then when we package that 1 basketball into this box, that is the lowest density when we compare the 3. So again, we had 3 same-size boxes, and we're packing different amounts of objects in there. That's going to affect the box's density. So to find density, we take the mass of all of our objects and we divide it by the volume of our 3D figure. So in geometry, mass is like the weight of our figure. And then for that volume aspect, we have a bunch of volume formulas on our reference sheet that we can use to help us find the volume if it's not given to us in the question. Now, density is a fractional value, right? We're doing mass divided by volume. So when we're doing our density units, since we're doing mass, which is usually in units of like grams, kilograms, and pounds, divided by volume, which is usually in cubic centimeters, cubic inches, cubic yards, cubic feet, our density units are always going to be fractional as well. So we might see it as grams over centimeters cubed, like in this example here, or it can also read grams per cubic centimeter, right? Whenever we see this word per, that's usually a dead giveaway that we have a density value or a density unit. So seeing it in this fraction will also tell us the units that our mass is in and that our volume is in. So if it's grams per cubic centimeter, we know that our mass is in grams, and we know that our volume is in centimeters. Now, not only is the volume in centimeters, but we know that all the dimensions of the figure would also be in centimeters. Now, this is going to be really helpful when there's going to be times where we have to figure out, hey, do we do a unit conversion or not? So you have to use the density value if it's given to see what units we're currently working with. So another example is kilograms per cubic inch. So again, this would tell us that our mass is in kilograms, and it would tell us the dimensions of the figure are in inches. And then last but not least, we can have another thing like pounds per cubic centimeter. And again, that would tell us that our mass is in pounds and our dimensions are centimeters of our figure. So make sure you're used to seeing, we might see fractional density units given to us, or we might see it in words. So just look out for that word per if you have it in words. So we also have population density. It's very similar, except population density is just going to be the amount of people you have divided by the area of your land. Alright, so for our first example, we're just going to be working with some word problems. We're going to see how to annotate it together. And in all of these problems, it's really either going to ask you to find the weight of an object, or it might ask you to find the cost of an object. And realistically, a shortcut you can use for all these problems, like 99% of the times it works if you just multiply all your values together. So I'll just show you what I mean by that. So in this first skill, we're going to work with finding the weight of objects, and we're going to work on identifying some variables in these word problems. Now, finding the weight of objects is a really important skill because it's going to be like your first step in a lot of these other word problems that we do. So let's go ahead and annotate. This is going to be the best thing that you can do to help you figure out what is going on. So a hemispherical water tank holds 523.599 cubic feet of water. That number is definitely important to us. If water has a density of 62.4 pounds per cubic foot, what is the weight of the water to the nearest pound? So we have a lot going on here. So the first thing we annotated was this number here. And the first thing that's standing out to me is that the units are in cubic feet. Now, we have 3 variables here, and this is the list that you guys should make every single time. DMV. Like you guys are at the DMV trying to get your license or your permits or whatever. So, whenever we have a unit of cubic feet or cubic inches with nothing else, that's a volume measurement. So our volume, we'll add to our list, 523.599, and we're adding our units in there. Then it also tells us the density. It's really nice that it lists out the density for us. But even if it didn't say that, if it just said 62.4 pounds per cubic foot, you would know that that's a density because you see the word per in there, right? That per is making it a fraction, and that's what density is, right? So our density, again, we're writing our units in there. We have 62.4 pounds, which is lbs, per 1 cubic foot. Now remember, density is mass over volume, so that the numerator tells you that your mass or your weight is in pounds, and it tells you that the dimensions of your figure are in feet. Now that works out really nice because look, our volume is also in cubic feet, so there's not any weird unit conversions happening here, so it's always good to double check that as well. Now we're looking for the weight. Now remember, for the sake of this course, the weight is going to be comparable to the mass. And now we're good to go. So we have our variables, we're just looking for m. Now it really helps to manipulate this diagram. So yes, d equals m over v, but if we want to find the mass, what we can actually do to get the mass by itself is multiply by the volume on both sides. And when we do that, we're going to get that your volume times your density is going to give you your mass. Now I'm just going to rewrite that in a different order. So m equals v times d. And let's just go ahead and substitute. And we're writing our units in. So our mass is going to be equal to our volume, which is 523.599 cubic feet. And we're going to multiply by our entire density. So that's 62.4 pounds per 1 cubic foot. Now a common theme throughout this whole entire lesson is that you're going to try to look for units or things that can cancel out. So right now I'm just going to put this over 1 so that we can kind of more clearly see what's happening here. And there's no unit that goes along with it. But you want to look for units that are in the numerator and in the denominator. So for example, what I see here is I see feet cubed in a numerator. I see feet cubed in the denominator, so that when this gets simplified, they're going to go away, right? So now I know the only unit that I have left is pounds, which is exactly what we want. We want our mass to the nearest pound. So what we're going to actually have to do when we multiply fractions, just remember we multiply straight across. So we're going to do 523.599 times 62.4. And that's going to give us 32,672.5776. Again, we're carrying our units back over, so we have pounds. Now, I'm not going to divide by this 1, because in the denominator, you just do 1 times 1. That gives you 1, and you don't need to divide by that. So, we have the exact unit we want, which is great, but we want to double check we're rounding it to the nearest pound, so our mass is just going to be 32,673 pounds. Now, in this next skill, we're going to use the same concept of finding the mass of our situation, but now we're going to be finding some costs. So again, annotating is going to be your best friend. We make our list of variables. Our list of variables, we have our D, M, and V, just like you're going to get your permit, and let's annotate. So a jewelry company makes copper heart pendants. Each heart uses 0.75 cubic inches of copper. Now that is a volume measurement, because we have those cubic inches. And it says, and there is 0.323 pounds of copper per cubic inch. That is a density. So 0.323, and it's lbs for pounds per 1 cubic inch. Now when we have our density, let's always just double check. So remember, D equals M over V. So that denominator portion over here is going to give you the unit of the dimensions of your figure. That's going to be cubic inches, and it's great because our volume is also cubic inches, so far we are good to go. Now, it tells us copper costs $3.68 per pound. Now, another good thing is that the cost is per pound. So if you take a look at the numerator of our density measurement, It's 0.323 pounds, right? So we can see pounds and pounds. There's no unit conversions. There's nothing crazy going on, so we're good to go. Well, if we want to find the cost, we need to know how many pounds our pendants are going to be. So that's going to be finding the mass, just like we did before. We did density times volume to give us our mass. But now once we have that mass, we have to multiply it by that price. Now, since there are 24 copper hearts, we're also going to have to multiply by 24 as well, because these first three things are going to give us the cost of 1 heart, and we're going to have to just multiply by 24. So again, typically, even if you have no idea what's going on, these are like common on the Regents exam. So when in doubt, just multiply all your values, be mindful of your units, and you'll get some partial credit there. So total equals, now our density is 0.323 pounds per cubic inch times our volume, which is 0.75 cubic inches, and I'm just going to put this over 1 just so it looks nice and uniform. But again, there's no units there because we're just putting it over 1 to make it pretty. So we have our density here times our volume times our unit price is going to be $3.68 per 1 pound. And then we're multiplying. We want 24 copper pendants, right? Now, I'm going to leave this at the very end. I'm just going to do the very beginning first so you guys can kind of see what I'm doing. Now, again, we want to look for any units that are going to cancel out. So I see pounds and pounds. That's going to go away. We also see in a different color, or we can use the same color, we see cubic inches and cubic inches. Those are going to go away. So the only unit that we're going to have left is money, which is what we want, right? We want the total cost. So the only unit we want to be there is dollars, right? So now we're multiplying our fraction straight across. So I'm going to put this 24 over 1, and we are going to multiply 0.323, which is here, times 0.75, times 368, times 24. And when we do that, we get 2,139.552. And again, remember, the only unit that we had left was dollars. And then in your denominator, you're just doing 1 times 1 times 1 times 1, so you don't really have to do anything there. Now, this is money, so you have to be careful here. You can't have 0.552 cents, so you have to actually round it to make it make sense with money. So it's 2,139.55 cents. And that's what it would cost you for 24 pendants. Now, if you just wanted the cost of 1 pendant, you wouldn't multiply by this 24. You would just do your density times your volume times your unit price. All right, now last skill. Same exact process applies, except now we're going to have some unit conversions. So we always have our 3 variables. I'm going to make my list over here so I have more room. We have D, we have M, and we have V. And let's go ahead and get annotating. So a machinist creates a solid steel part for a wind turbine engine, and the part has a volume of 1,015 cubic centimeters. So our volume is 1,015 centimeters cubed. Steel can be purchased for 29 cents per kilogram and has a density of 7.95 grams per centimeters cubed. Now again, we know that this bottom unit is for our volume. So our volume is in centimeters cubed and the density thing is in centimeters cubed. So far we're good. However, the cost is given to us per kilogram, but then the mass that's given to us, like the mass unit in our density, is in grams. So we have kilograms and grams. We know there's something funky happening. We're going to have to do a unit conversion. Good. And it says we're making 500 of these parts, and we want the cost to the nearest dollar. So we are going to do a unit conversion because our mass is in grams, but the cost is giving it to us in kilograms. Alright, so our total is going to be equal to our density times our volume times everything. We're multiplying everything together. So 7.95 grams per cubic centimeter times our volume, which is 1,015 centimeters cubed. I'm just going to put that over 1 to make it nice and pretty. Times our unit price. Our unit price is 29 cents per 1 kilogram. And then I'm going to multiply by that 500 after. I'm just going to multiply by our unit conversion as well. So now let's just figure out what units are going to cancel and what isn't. So we have centimeters cubed is going to cancel out. We have that in a numerator and in a denominator. But we have these grams and these kilograms that need to go away. So I see grams in the numerator And in order to cancel it out, I know that the grams needs to go in the denominator. That's the only way I'm going to get it to cancel out. I also need this kilogram unit to also go away because I'm looking for a cost. So the only unit I want is this money sign right here. So I also need to know that our kilograms are going to be in the numerator up here. Now this prefix kilo means 1,000. So 1 kilogram is equal to 1,000 grams. And that's going to be our unit conversion right there. So now we have kilograms and kilograms, that's going to go away. We have grams and grams, that's going to go away. And then we're just left with dollars, which is what we want. We're looking for a cost, right? So now it's going to change a little bit because in previous examples, we didn't have to really multiply our denominators by anything, right? We just had 1 times 1 times 1 times 1. But now in our denominator, we're going to have 1 times 1 times 1 times 1,000. So let's do our numerator first. We're going to do 7.95 times 1,015, or times 0.29. That's going to give us 2,340.0825. And again, that's dollars, right? Divided by now, we have 1 times 1 times 1 times 1,000. And notice all of our units are gone. So we're just going to divide that number by 1,000. So we get 2.34. Now what that represents is the cost of one of the parts. And that's why, remember at the end, before we did this too, we got to multiply by that 500. So we're doing times 500. And I didn't do that in the beginning because I wanted you guys to really see how the units come into play and how we start canceling those out. But from the beginning, if you wanted to put that times 500 in there, you'd be good to go. So we're going to do 234 times 500, and we get $1,170.04. But we're rounding to the nearest dollar, so it's $1,170. And again, always step back and think about this represents the cost for 500 parts. Okay, so you guys want to just be mindful of your unit conversions. You want to make sure you're mindful of those prefixes like kilo. That's a common one that we use. Kilo means 1,000. And again, in this, right, I kind of figured out where my units had to go based on what had to be canceled out. So grams was in the numerator. I knew it had to be canceled out, so I had to put it in the denominator over here. And then kilograms is in the denominator, so I knew I had to put it in the numerator for it to go away. So when in doubt, just multiply all your values. Make sure you're annotating your questions and putting your units in there, and you guys will be good to go.